later. All right, and we are live. So the lesson for today, like I said, is going to be on trig identities. We're on lesson number 25 of pre-calculus. Here's an example of a problem we'll be able to solve by the end of class. So basically, we're taking an expression and we're going to simplify it into one single trig function that will say like this is sine, this is cosine, this is tangent, this is cosecant, or it'll just be an expression. So we're simplifying trig expressions. It's gonna be a lot of fun. It's gonna be a lot of algebra. If you enjoyed the solving rational or inverses of rational, then you'll enjoy this topic. So that's kind of where we're headed for today. All right. It's been a long time since we did a brain teaser, so I thought I'd give you a brain teaser. So think about this question. Send on the chat what the answer is. I'll give a virtual ticket to whoever can answer first. So the question is, what goes through a door but never goes in or out? Close, Michael. Close. But that stays outside. What goes through a door but never goes in or out? Yes, that is correct, Michael. She sent me a note privately. The answer is a keyhole. A keyhole goes through a door but never goes in or out. All right. As we always do in class, we say the four goals. So I'll just say them here. We will learn math, build character, never give up,
Never give up.
and ask why.
Ask why.
Awesome. That last one is particularly important here, that we ask questions, just given the fact that I can't see y'all and y'all can't see me. So we'll just keep that in mind. All right. So a trig identity, you should either have the notes printed out or you should have a sheet of notebook paper to write on. You kind of want to shorthand if you're using a sheet of notebook paper, kind of like college. Just write what's the important information, not all of the information. Okay. So by definition, equation is considered an identity. So we're talking about trig identities. I just want to define what an identity is. Considered an identity if the left side is equal to the right side for all values of the variable for which both sides are defined. A lot of words there. Let me just kind of clarify that. So this right here would be an example of an identity. It is an equation, has an equal sign, it's an equation. The left side is equal to the right side for all values for which the variable is defined. What that means is, if you were to plug in any number for x here, let's say I plug in 1, and 1 here, and 1 here, the left side would equal the right side. If you were to plug in 2, the left side would equal the right side. The reason why it says where they are defined is because there is one value in which x is not defined. That value will be 3, right? Because if you plug in 3 on the denominator, 3 minus 3 would be 0, and then you will be dividing by 0, and that is undefined. So it can still be an identity if you have some values in which it is undefined, but every other x value would be defined, okay? So by definition, an identity is where the left side equals the right side for all values of x, but you're not including the ones where x is undefined. If we just think about this, the reason why that's true is because you could factor the top, by the way, to x plus 3 and x minus 3, right? And the bottom will be x minus 3. That will cross out. So you just end up with x plus 3. And then you have this over here, x plus 3. So it's the same on the left and the right side. So therefore, any number you plug in for x is going to be true, right? Because the left side already equals the right side. The only one that is not true is right here at 3, because you're going to have a missing value that is going to be undefined, okay? So that's by definition what a identity is. When we talk about trig identities is basically ones in which it would be, change this color. Trig identities would be one in which you're including sine and cosine, and the left side equals the right side for any value that you plug in that it is defined. So for example, let's say x is 0, okay? Sine of 0, let's try this. That would be, sine of 0 would be what there? What's sine of 0? Get some feedback here. Sine of 0? 0, yes. Right here, right? 1 comma 0. 1 minus cosine of 0 is
1 minus 1.
That's true, right? Okay. But if we try pi over 4, 45 degrees, okay, we plug that in here. Sine of pi over 4 is equal to what?
Square root of 2 over 2.
Okay. And then we have 1 minus cosine of pi over 4 is also square root of 2 over 2, right? Is the square root of 2 over 2 going to equal 1 minus the square root of 2 over 2? Is that going to be true or false?
False.
That's going to be false, yes. So it's false. Is it undefined there, or is it just false?
It's just false.
It's just false. So therefore, this is not an identity because it has to work for every x value. So when we're talking about trig identities, okay, like going back to the beginning like this, for example, let's say that this was a trig identity, okay? Not saying it is, but let's say it was. Then that would mean anything that you plug in for x, anything except for where it's undefined would be true, okay? If you had something on the left side, that is, like let's say you had this. Anything you plug in for x on the left side and the right side would have to be true. Any questions so far? I'm gonna pause and allow you to ask questions in the chat or ask questions via voice. Just talking about definition of an identity. An identity is where the left side equals the right side for all values of x in which it is defined. Any questions thus far? Okay. All right. So here are some examples. I see my computer is lagging again. There we go. Here are some examples of trig identities, okay? Some of these are on your formula sheet. Some of them are not. These are really crucial for calculus to know these and just kind of know the patterns, okay? You're going to use these quite a bit in calculus. So a couple of these we already know or have talked about. A couple of these are new, okay? We've talked about, this one is not on your formula sheet, by the way. Quotient identities. It's not on your formula sheet. However, it's something we've talked about before. We know that we talked about the last class or last video session, right? Tangent is sine over cosine. So it's not on your formula sheet. However, that is something that we know. Cotangent is the opposite of tangent. So therefore, if you flip this, it's going to be cotangent, right? So cotangent is cosine over sine. So you just kind of have to know those. That is our quotient identities. All right. By the way, if you don't print the notes and you're using a sheet of notebook paper, what I would recommend is that before the class lesson that you write out kind of the things like this, so that you're not writing it as we're talking about it, so you can focus on what we're talking about. So if you're not able to print the notes and you're doing handwritten notes, I would since I post them the day before, I would use that to look at beforehand. So that way you have kind of some of the baseline already filled out instead of copying all this down, all right? So the quotient identities is not on your formula sheet, okay? But we talked about that. You just got to know those. These are on your formula sheet. There's not going to be a formula sheet where these are on for calculus, but just for pre-calculus, that is on your formula sheet. So these are the reciprocal identities. We talked about these, just the opposite. So sine is the opposite of cosecant. Cosecant is opposite of sine. Sorry about Zane. Pythagorean identities. Pythagorean identities, we talked briefly about this one. We're going to talk more about these two, which we haven't touched. Those are all identities, okay? So we're going to explore a little bit of these more today, okay? Any questions thus far? All right. All right, so here, let's just kind of first start with this should say reciprocal. I'm sorry, to say reciprocal. I made a typo even online, y'all. I guess it's just inevitable. So let's just say reciprocal. So let's say we want to find this. It says if cosecant of an angle equals 7/4, and we're trying to find sine of that particular angle. Now, the way we used to do this before would be we would kind of graph a triangle, right? And we would say, okay, this is the angle. We would say cosecant is the opposite of sine, so it's hypotenuse over opposite, right? And we would put hypotenuse 7, we would put opposite 4, and then we just find what sine is, but it's really just the reverse, right? So if you remember, we would do these with like, if cosecant is that and sine is less than 0, what is tangent of the angle? Kind of like those type of problems. So here is just a basic example. So we have cosecant and it's trying to find sine. Sine is just the opposite, so we can know it's just that flipped. But I just want to talk about the relationship between this and the reciprocal identities here. So cosecant is up here, right? Cosecant is 1/sine. So if we put that, cosecant of the angle is 1/sine of the angle. I'm sorry, actually, let's use, rewind it back. Let's use this one, actually, I'm sorry. Let's use this one right here. It's not letting me zoom out. Okay, let's use this one right here. So sine of the angle. So sine of the angle equals 1/cosecant of the angle, right? And so cosecant of the angle is that. So we can replace that with 7/4. So it'd be 1/7/4. And when we have 1 divided by 7/4, if we were to do the longhand math and do keep, change, flip, and all of that, it's just going to flip the 7/4. And we need to be able to recognize that so that every time we see this, we're not actually doing keep, change, flip, and dividing. So this is going to equal 4/7, okay? The reason why that is, if you want to see it, 1 divided by 7/4, this is 1/1. Keep, change, flip, this would be 1/1 times, that would flip to 4/7. So it's going to be 4/7, right? And so I would like for us to be able to see, okay, if I have 1 divided by that, that's the reciprocal. It's going to flip what's on the bottom. It's going to become 4/7, okay? So which we can just see at the beginning, right? Cosecant is that, sine is the opposite of cosecant, so it would just be 4/7, but I want to just kind of help us to see where that reciprocal identity is coming from, okay? And that's the same case for all of them. All of these are going to be the opposite of each other, okay? The other one is the Pythagorean identity, which is the first of the 3. Sine squared plus cosine squared equals 1. We touched on that and before the break. So that just comes from the unit circle. If we remember, the unit circle, the hypotenuse is 1, right? Cosine is x, sine is y. And so if we think about the Pythagorean theorem, a squared plus b squared equals c squared. And so that if that's a, b, and c, it would just be like this squared plus this squared equals that squared, which is what we have here, right? Cosine squared of theta plus sine squared of theta, that's like saying a squared plus b squared equals c squared, which c is just 1. And so that's just going to be 1 equals cosine squared of theta plus sine squared of theta. That's this Pythagorean identity there, okay? Now, with that, you could write it either way, cosine squared of theta, like I have here first, or you can have sine squared of theta first because it's adding. If you do 3 plus 4, 4 plus 3, it's going to be the same thing, 7, right? With this, it's important to note, we need to be able to see the patterns. So these would also be true based on what we have there, right? Because if you take that equation, cosine squared of theta plus sine squared of theta equals 1, and let's say that you just like solve for sine squared. So let's say you subtract cosine squared of theta. You would get sine squared of theta equals 1 minus cosine squared of theta, right? So that is also true, right? That is also an identity. And we're going to use this later where we use this pattern right here. And you could do the same thing. You could solve for cosine. And if you solve for cosine, you'll end up with that, right? And so it's not on your formula sheet. These two are not on your formula sheet, but they can be derived from this one up here. So it's important to note that that identity, sine squared plus cosine squared equals 1, can be also rewritten and solve for either cosine or solve for sine, okay? So that's that first Pythagorean identity. Let me pause there and give you a minute to collect your thoughts there, right, if you need to, and ask questions if you need to, or comments. So let me just pause there for a second. Anything I need to go back and explain, anything that anyone's confused about? Again, I can't see your faces. Usually in class, I see your faces and I can tell whether you got it or you're tracking along. So any feedback there in the chat or comments would be helpful for me to know if we're on track. Or you can unmute yourself. All right, so far, okay. All right, so let's talk about the other two now then. We have 1 plus tangent squared of theta equals secant squared of theta. That's new, we haven't talked about that. 1 plus cotangent squared of theta equals cosecant squared of theta. So where do those come from? How can we prove that these are true? And by the way, just kind of rewinding it back for a second, when we talk about this Pythagorean identity, that means any angle you put in here for theta, like if I put 30 degrees here and 30 degrees here, when you actually do the math, is going to equal 1, right? Or if I put 60 degrees here and 60 degrees here, when you do the math, is going to equal 1. So any value that you plug in for that angle, unless if it's undefined, is going to be true all the way across the board, okay? That's what makes it an identity by definition, and what makes a statement true in these cases. These are special cases which is always going to be true, okay? So let's talk about these two. We're going to prove where those two come from, and then we're going to start simplifying, okay? So why does 1 plus tangent squared of theta equals secant squared of theta? Okay, why is that is the case? So what we can do here is we can use our identities, we can use our reciprocal identities to kind of rewrite these so that we could see why this is true, okay? So what I mean by that is, let's say that we want to rewrite tangent squared of theta only with respect to sine and cosine. How can we rewrite, and this is a question I'd like for you to answer, how can we rewrite tangent squared of theta using what we know? So how can we rewrite tangent squared of theta? What identity could we use from before? Okay.
Sine squared of theta over cosine squared of theta.
Okay, very good. So sine squared of, because tangent is equal to sine over cosine, right? And so we can rewrite this as, it's squared, so it would be sine squared of theta over cosine squared of theta, okay? And as we still have this 1 over here. All right. Then we have the secant squared of theta. What identity can we use to rewrite secant squared of theta?
1 over cosine squared of theta.
Very good. 1 over cosine squared of theta, because secant of theta is equal to 1 over cosine of theta, right? That was a reciprocal identity. Okay, so we need to kind of like see these and like see the patterns in our head where we can apply them. Okay, now we're gonna do some algebra here from now, and basically see that this statement is true. Okay, so in doing that algebra, what we need to do is we need to look at this here, and we need to simplify it. Okay, so if we have 1 plus sine squared of theta over cosine squared of theta, we're gonna combine that together first, and this is where we need our fraction knowledge. So when you add these, first let's go ahead and write this as 1 over 1. When you add fractions, they have to have the same denominator, right? And so the left side, 1 over 1, needs to have the denominator the same as this. So we will be multiplying, I can't really, I ran out of space. We're gonna do cosine squared of theta over cosine squared of theta times that 1 over 1, okay? And remember, when you multiply, you have to do the top and the bottom here, because that's still equivalent to 1. So we're just multiplying everything by 1. Plus sine squared of theta over cosine squared of theta, and we still have this over here. Okay? When we multiply this, it's just going to stay the same. All that's staying the same. Give you minutes to write that so far. So all we did was we rewrote, just to recap, we rewrote tangent, we rewrote secant using the identities we know. Now we're getting a common denominator so we can combine what's there on the left side. And then when we add fractions, we have to remember, like if I'm adding 1 over 3 plus 2 over 3, the denominator stays the same, right? And the numerator you add, so that's like 3. So the same concept here. When we want to add this, the denominator stays the same. So it'll still be cosine squared of theta. The numerator you add, but we can't add cosine and sine, so we're just going to leave this as cosine squared of theta plus sine squared of theta. I'm going to move this over here. So we have, this is where we have to remember our identities. We can rewrite cosine squared of theta plus sine squared of theta as what?
One squared.
Close. Just 1, because it's sine squared of theta plus cosine squared of theta equals 1, right? So it's going to be 1. And then this, I'm just going to rewrite. This I'm going to rewrite. And then beautiful, is that statement true? Is 1 over cosine squared of theta equal to 1 over cosine squared of theta? Yes, it is. And so therefore that proves that this is a trig identity, and that is why it works. Just showing you where they come from right now. We'll use them and apply them in a second. Showing you where they come from. So that is where, now we talked about this one right here, right? Talked about that one right there, proved that one. Any questions so far? All right. Cool. Let's talk about the third one then. this one right here. So let's prove that one. And then we will go ahead and simplify, okay? So 1 plus cotangent squared of theta equals cosecant squared of theta. So that is the third Pythagorean identity, okay? So for that one, if we want to prove this, it's easy always to kind of write things in terms of sine and cosine, because then you can kind of combine and things like that. So if we want to write this in terms of sine and cosine, how could we rewrite cotangent squared of theta?
Cosine squared over sine squared.
Very good. Cosine squared of theta over sine squared of theta, because it's the opposite of tangent. And then how could we write cosecant squared of theta?
1 over sine of theta.
Very good. Wait, 1 over sine.
Of theta?
1 over sine, close?
Squared of theta.
All right, very good.
Um,
Because we got a square there. All right, then we got this one right here. Okay, now we're looking at this. We're seeing, okay, how can we simplify this? So this is very similar to the other one, right? We want to get a common denominator. So we're going to write this as 1 over 1. We're going to multiply this one by sine squared of theta over cosine squared of theta. So that we can, or where did I get that from? Over sine squared of theta, sorry. Wind it back. Okay, and so we're going to get, we'll multiply this sine squared of theta over sine squared of theta plus cosine squared of theta over sine squared of theta. All that's going to remain the same. And then we can see that this is very similar to what we had before. We're going to end up with, when we add fractions, the denominator stays the same. The numerator, you can add that. Beautiful. And we see a Pythagorean identity here, right? We see that sine squared of theta plus cosine squared of theta is equal to 1. So we have 1 over sine squared of theta equals 1 over sine squared of theta. And that is true. And that is why the third Pythagorean identity works. All right, beautiful. Having fun yet? We're just getting started. Questions? All right, all right. Now, what we're gonna do here in a second is we're gonna actually simplify them like the first slide. But one thing to take note, again, when we're simplifying, we're gonna be looking for patterns. We can see on here, these are the original ones, and we just proved why they are the case. This one we proved from the unit circle. This one we proved by simplifying it and the left side equal the right side. This one we proved by simplifying by converting the sine and cosine, and then the left side equal the right side. But one thing to note and to remember is that they're not always going to be written explicitly in this way. So they could also be written. Can y'all hear Zane? Sorry. It can be written like that, right? Or it can be written like sine squared of theta equals 1 minus cosine squared of theta, right? It can be written like that. So what I would do later is I would write next to this one, these two as well, because when we're solving, you're going to be looking for patterns. So like, let's say you see this. And then you're like, okay, how can I simplify this? What can I do next? You would want to be able to see that this you would write as cosine squared of theta. You see what I'm saying? And so you want to be able to see that pattern. Okay, so I would make sure you have those as well. Now the same can be said for this, okay? So even though that's one identity, you can manipulate that identity. You can say, okay, if you just move this over, it would be 1 equals secant squared of theta minus tangent squared of theta. So anytime we see secant squared of theta minus tan squared of theta when simplifying, we can change that to 1. Give me a minute to write that down. All right. So we would need this one as well, right? Or let's say we move this around a different way. We can also move the 1 over, right? And tangent squared of theta, we can say equals secant squared of theta minus 1. Y'all see what I'm saying? So there's different kind of patterns. You could write this one down and say, okay, if I see secant squared of theta minus 1, I can change that to tangent squared of theta. Okay? So we'll get more into that later, but this is just for you to know. You want to write the different combinations that could come up just by moving one thing to the other side. Okay? It would be the same thing over here. You could subtract cotangent squared of theta. And so that means 1 equals cosecant squared of theta minus cotangent squared of theta, right? Or you can move the 1 over, and it would be cotangent squared of theta equals cosecant squared of theta minus 1. Okay, so there's different combinations here of these kind of principal identities, okay? I'm gonna pause there and give you a minute to write down what you need to. Do we have any questions before we talk about simplifying? Okay. Let's jump into simplifying. Okay. So with simplifying, there's it's going to be. Oh, hold on, let me fix this. Sorry. With simplifying, there's going to be kind of some basic strategies here. I like to think about this as kind of like a puzzle. Okay. And you want to try different things to kind of make the puzzle work. And sometimes you need to start back over, and so these are just some tips. Okay. Number 1, it's helpful to express the expression in terms of sine and cosine, kind of like what we did at the beginning. Like we had this, we express that in terms of sine and cosine. Okay. Number 2, another tip is use the known identities that you have for the purposes of substitution. What I mean by that is, let's say you have sine squared of theta plus cosine squared of theta in your equation. You want to use that identity, go ahead and change it to 1. So I would have all of the identities next to you as you work through the problem. So I would have the quotient identities, tangent equals sine over cosine, cotangent equals cosine over sine. I would have the reciprocal identities, cosecant equals 1 over sine, and all of those. I would have the Pythagorean identities, these 3 right here. I would also have the kind of manipulated Pythagorean identities, when you move stuff around within them, what they equal. So those, I would have them next to you, and anytime you see them, simplify. Third, if there are fractions, get a common denominator. You saw us do that in the proving examples. Get a common denominator, combine. Fourth, use algebraic factoring, distributing, all of those kind of algebraic skills we know. All right. Fifth, if a strategy doesn't work, go back to the drawing board and start over. Okay, that's just some tips. Again, it's like a puzzle. You're gonna do the problems and you'll kind of see what I'm talking about. All right. And then you don't really want to write sine squared of theta like that. It's just as a shorthand, we would just write sine squared of theta. Okay. So you don't really write cosine squared of theta like that. You write it like that. So that's just a simpler way of writing it. Okay. So these are some tips and strategies. So let's jump into our first one. We're going to do 4. Okay. We're going to do 4 and then the practice after that. So let's say we want to simplify this. Okay. We're going to have a little bit of, we'll start with the easy example here. We're going to simplify this into a single trig function. So we have tangent of x cosecant squared of x minus tangent of x. And we want to take that and simplify it, okay? We're going to try to use, okay, that's better. We're going to use strategy number 1. We're going to try to express this in terms of sines and cosines. That's kind of the best, my favorite strategy is the easiest in my opinion and probably most generally applicable. So we're going to express tangent in terms of sine and cosine, and I'll ask for your feedback as we do this. How can we express that in terms of sine and cosine?
Sine of x over cosine of x.
Okay, sine of x over cosine of x. Good. And it's being multiplied by cosecant of x. How can we do cosine of x? Or cosecant squared of x in terms of sine and cosine?
1 over sine squared of x.
Okay, good. And then minus, how can we express tangent of x in terms of sine and cosine? Oh, that's the same as the first one, right? Sine of x over cosine of x. Okay? So we express everything in terms of sine and cosine. Once we do that, we kind of say, okay, can we simplify anything, right? So what do y'all see here that maybe we could do? Ideas. Ideas on what we could do here. Simplify this.
Multiply the first two.
Okay, so we multiply the first two. We want to keep in mind PEMDAS here, right? So like you can't subtract before you multiply, right? We're doing PEMDAS. So let's multiply the first two. So at the top we'll have sine of x over cosine of x sine squared of x. And we're just kind of trying some algebraic stuff we know and just trying to kind of get it to simplify. Okay. Now, we want to simplify the work as much as possible. So we could go ahead and subtract this and get a common denominator, but that would entail multiplying this by sine squared of x over sine squared of x. And it wouldn't necessarily be wrong to do that. But I want to see here, I can see something that would simplify our work, right? What's another way to rewrite sine squared of x? We could write that as sine of x times sine of x, right? There's 2 of them. That's what that means. And so because of that, we can go ahead and cross out the sine of x at the top and the sine of x at the bottom, right? Because sine of x divided by sine of x is equal to 1. Anything divided by itself is 1. 5 divided by 5 is 1. 4 divided by 4 is 1, right? So that we can cross that out. So earlier, when I see this right here, what I would do is I would say, okay, I'm going to go ahead and cross this square out with this, right? Because you're taking away one of them at the bottom and with the one at the top. And so then you just, or you could do it here as well, cross that out with that. Or you can just write it out if you need a visual, sine of x, and then cross it out, whatever way works for you. And then at the top, we'll have a 1 times cosine of x, sine of x, minus sine of x over cosine of x. Okay? So this just simplifies it for us a little bit, all right? Then we can't cross out. We can't cross this and this out, okay? We want to be careful of that because there's a minus sign here. All right, it's only when it's multiplication. Because multiplication brings it all together and then you would cross out on top. Subtraction is separate. Okay, so then we need a common denominator. So now we're using, okay, we're going to use a number 3 strategy. There are fractions, gain a common denominator. So to do that, I'm going to multiply this one by sine of x over sine of x, because that's what it's missing that this one has. So that is going to equal 1 over cosine of x sine of x. Let me actually move this up here. 1 over cosine of x sine of x minus sine squared of x, that's multiplying this times this, over cosine of x sine of x. All right, common denominator, we have that, so we can keep the denominator, cosine of x sine of x. The numerator, we can put 1 minus sine squared of x. Notice we subtracting them because there's a minus sign. All right, now here is where we see, okay, can we do anything else? I want us to kind of think about this. Is this completely simplified? We got it simpler than, you could say, simpler than it was. It was like that originally, right? Can we do anything else more with this? Ideas. Ideas. Well, let me tell you, we can. So what?
So
Can you come
for the 1 minus sine squared of x, like the isn't that like for the first Pythagorean identity? But then, like if you take the first Pythagorean theorem and then you subtract sine squared of the angle, isn't it that like
Like that, right? That's what you're talking about?
yeah
Beautiful,
yeah
yes. So we can change this to what then?
cosine
Yeah.
squared of x?
Very good. Very good. Yes. Y'all see that? Let me put x here because this is x. So that's where that strategy, having the known identities next to you and using them for substitution will help. Okay. So we see that pattern 1 minus sine squared of x just to make us think, okay, 1 minus sine squared of x is related to that trig identity, and that trig identity is going to help us to get that simplified. Okay. So let me write that because it looks a little messy. Cosine squared of x. That's not a square at the bottom. I'm sorry. That's just cosine of x. Sine of x. Okay, beautiful. What else? What else do we see? Do we see anything else?
The squared on the top,
Mm-hmm. This?
cross it out with the bottom one.
Good, because this means we have 2 of these, right?
Yeah.
If we have 2 of them, we can cross out one of them with one of them, okay? So what are we left with then?
Just cosine of x over sine of x.
Beautiful. Do we see anything else? Please don't say cross out the x's.
That would be cotangent.
Yes, very good. This is cotangent of x. Beautiful. And that is what that equals. So we simplified it into a single trigonometric function. Wasn't that fun?
Yes.
We're going to try a couple more. It's kind of involved. And so I want to do a few practice problems together so that when you kind of do it on your own, you're not like, I don't know, I'm stuck here. Any questions, comments, confusions? Or you can just say I'm having fun. Questions?
Oh shit, I'm not writing shit.
What's that? I didn't hear what you said.
Oh, nothing.
Okay. Yay, Leah. Yay, Jimena. Anybody get lost anywhere? Okay. If not, let's try. We're going to try 4 total together, okay? And then I'm going to let you kind of mess with this on your own. And then tomorrow at 10, we'll do a tutoring session Zoom. It won't be a new lesson. And then we'll use that. Thank you, Fabian. I think it's cool too. We use that for help with any of the problems you have, okay? So this one is, matter of fact, actually we're gonna skip this one, and let's actually, I'm gonna have you do this one at the end, and just to make sure you feel comfortable, and then I'll go over it after. Okay, so we're gonna come, because that's very similar to that. We're gonna do this one actually. Okay, remind me at the end if I forget to come back to that one. Okay. So let's say we want to simplify this. This one says simplify it into a trigonometric function with no fraction. So this one, the goal is still to simplify, but this one is saying simplify with no fraction. Okay. So in this case, it looks pretty simple already, right? All we have is a 1 and a 1 plus cosine of x. I want to look at this and I want to say, okay, let me just make sure this can't be related to one of these, okay? And it can't, but we just want to always look for that, because let's say that it was, it could be, then you would want to go ahead and convert it, right? Like let's say this was 1 minus cosine squared of x, then we could convert that to sine squared of x, but we can't in this case, right? So what we can do, is we can use if you remember conjugates with radicals, it's just kind of taking us back a little bit. But if you remember with, trying to give you an example, let's say you have 1 over, this is also with I. So you have 1 over 1 minus square root of 3, and you wanted to get rid of the radical on the denominator. Does anybody remember what we multiplied by to get rid of the radical on the denominator by any chance? This is taking us way back. No? Okay, it's all right.
No.
It's all right. It was 1 plus radical 3 over 1 plus radical 3. It's a conjugate. So you're just changing this to a plus, okay? Because what happens is it becomes like a difference of squares. When you FOIL it, and you don't have to write it down, I'm just going to kind of show you this. This becomes 1 plus square root of 3 minus square root of 3, and then that becomes minus, and the square root of 3 times the square root of 3 is 3, and then these cross out, and it's just 1 minus 3, which is negative 2, right? That's that conjugate. That's using kind of the similar principle of, like, let's say you had, let's say you had x plus 3 and you multiply it by x minus 3, okay? When you FOIL, you get x squared minus 3x plus 3x minus 9. These two cross out to 0, right? So then you just have x squared minus 9. So there's this general kind of principle here that when you see this, you want to think about this. If 1 is plus and 1 is minus, and you're multiplying, what ends up really happening at the end is that it ends up being what this times this is your first term, and this times this is your last term, because everything in the middle crosses out. And so you kind of have to apply this concept here on this by thinking about it this way. If we make this become 1 minus one minus cosine squared of theta. If we make that become 1 minus cosine squared of theta, then we will be able to convert that to sine squared of theta. Okay, using this identity. All right, and the only way to do that is by multiplying this by 1 minus cosine of x over 1 minus cosine of x, okay? Because what's going to happen is at the top, we'll have 1 minus cosine of x. And at the bottom, when we FOIL this, I'll just do that off to the side, but 1 times 1 would be 1. 1 times that would be minus cosine of x. That would be plus cosine of x. This would be minus cosine squared of x, right? And this is gone. So it's 1 minus cosine squared of x. Okay? Or we can just see this times this gives us this. And this times this gives us that. And we'll talk about, we'll see why that helps us. But any questions so far? Basically, the basic idea is we're multiplying by the opposite. So if it's 1 plus cosine of x, we'll multiply by 1 minus cosine of x, the conjugate. Did I lose anybody there? Okay. What can we convert this to now? Just the bottom part.
Sine squared of x.
And that's using that identity that Chatambi talked about earlier. That's from this one, right? Minus
X
cosine.
is T.
Huh?
It's X, not theta.
Oh, keep wanting to use theta. Thank you. Thanks. So that's using this identity. And then the top, we can't do that with the top because the top doesn't have a square on it. Okay? 1 minus cosine of x does not equal sine of x. Okay? Now, our end goal was to simplify this and to get no fraction. However, over here we had 1, 2, 3 terms, and over here we have 1, 2, 3 terms. We haven't really simplified necessarily, and we haven't gotten rid of the fraction. So what does that help with? What that helps with is that, and this is important to note, if you have 5 over 3 plus 4, let me make this easier actually. If you have 8 over 2 plus 4 versus having 2 plus 4 over 8, okay? This is important to note. In the first example, you can not do this 8 divided by 2 plus 8 divided by 4. You cannot do that, okay? But in the second example, when you have it at the top like that, you can split that up into 2 over 8 plus 4 over 8, right? So if you have a single thing you're dividing by, you can split it up, but in the first example, where it's 2 things at the bottom, you cannot, okay? So that's going to be helpful here because what that allows us to do right here is you applying this principle, we can separate this into 1 over sine squared of x minus cosine of x over sine squared of x. Okay. Let me pause there. Questions, comments, confusion? Okay. Then we can change this to what? To get rid of the fraction.
Cosecant squared works.
That's that identity, the quotient identity, right? Now we got rid of the fraction. That's our goal here for this problem. And then this over here, we can rewrite that as having cosine of x over sine of x times sine of x. There's two of them, right? Okay. So what we can do there in this case, because there's not a plus sign separating them here, we can divide them each to get rid of the fraction. Okay. So cosine of x divided by sine of x is what?
Cotangent.
Mm-hmm. And then it's not a plus sign here separating it. So we can do this cosine of x divided by sine of x. That's going to be what? I'm sorry. We're one. No, there's a 1 over here. I'm sorry. 1 over that. We already divide the cosine by the sine.
Cosecant.
Cosecant.
Mm-hmm. So we divided the cosine of x by the sine of x, and then the 1 by the sine of x. And we have gotten rid of the fraction. Now, is there anything else we could do with this? That one you got to kind of look for. And look at that and look at the strategies. We've expressed it in terms of sine and cosine already. We've used our known identities for substitution. We haven't gotten a common denominator, but that wasn't necessary here. Have we used all algebraic factoring distributing principles that we could apply? Okay, bye, Sophia. I'll upload this so you can see it. Take care. Any ideas? Think about this. What could you do with this? Factor, yes. Like you would factor x out of this, right? And so similarly, out of this, we could factor what?
Cosecant.
Mm-hmm. So we take out cosecant of x, we'd be left with 1 cosecant of x minus cotangent of x. Can we do anything else, or is that done? I know we've simplified it. I know we've gotten rid of the fraction, but we want to see, can we do anything else here? I know y'all can find it. I see something. Go back to the strategies.
Cosecant of x minus cotangent of x equals 1.
Very good. Where do you see that from?
From the Pythagorean identities.
Which one?
1 plus cotangent equals cosecant squared, that one.
Very good. So if you weren't able to see that, that's where I was saying earlier, it's important to write all of the different types, because I can look at this and I can say, okay, I see a cosecant here, a cotangent here, right? Oh,
But
I lied.
don't they have to be squared?
I lied. Yes, that's squared. Sorry. If this was squared, you could do that and that would have been beautiful, but I think we're done here. Sorry. Yes, we can't do that because it's not squared. If this was squared, we would rewrite that as 1, but it's not squared. I meant to make that problem squared so that we could see that. If that would be a case in which you would apply it though, but we can't. So I think we're actually done here on this problem. All right. This is why it's important to do the live chat, I guess, because I make mistakes sometimes and typos and stuff, and I would just keep going, and y'all be watching the video like confused, like, Mr. T, what are you doing? All right. Any questions? All right. We'll do one last one together, okay? Because I want to make sure you feel confident doing these on your own, because it's kind of involved. This is from the very first slide, the end goal, right? This problem here, okay? So we want to simplify this into a single trig function. It's just kind of putting it all together, all right? So now with these problems, you might start something and doing it a certain way and then realize that that strategy doesn't work. And then you got to start over with a different strategy, and that's going to be okay, okay? That's going to be okay. So we're going to try a different strategy, see what works, okay? So looking at this, everything is already expressed in terms of sine and cosine. So that's good. Don't got to change that. We can go ahead and try to get a common denominator. We just kind of try to do strategy number 3, okay? So they both will need a common denominator. So what would we need to multiply this one on the right side by? So what would we need to multiply the one on the right side by to get a common denominator? Okay, good. 1 minus sine of x. And what would we need to multiply this one by? Cosine of x.
Sine of x.
Mm-hmm. Okay, so now we have the same denominator. So now we need to kind of distribute. Take note that these are together. They are being multiplied. So when you distribute it into that, you don't need to distribute it to the sine and to the cosine. You distribute it, it's just going to be sine of x times cosine squared of x at the top. Bottom is going to be cosine of x times 1 minus sine of x, right? Okay. Now over here, we should notice the pattern that we talked about earlier. We are multiplying by something that is the conjugate. This is 1 plus that, this is 1 minus that, right? So if you want to, you can multiply it out with FOIL or box method, right? And you can do all that. Or you can just notice a pattern and know, okay, what's going to happen is going to be that squared and that times that, right? Because 1 times 1 is 1, and then 1 times that is negative sine of x. That's going to be plus sine of x, but then at the last part, you're just going to have minus sine squared of x, and these cross out. So if you can see that, you can see that, and you would just do 1 times 1, 1, and then sine of x times negative sine of x, sine squared of x, right? Denominator stays. We're going to have 1 minus sine squared of x. Okay. Our goal is to simplify into a single trigonometric function. Presently, we have gotten a common denominator. Now, what next? Ideas. Remember, there's ways we go bad and we realize, okay, maybe this will work, maybe this won't work. Ideas on what we could do here.
For the first part, cross out the squared and the cosine of x.
These two?
Yeah.
Where did this square right here come from? That came from us doing what?
Oh, okay. Yeah.
That'll be reversing what we did, right?
Yeah.
We would do that if that was our final step, yes.
1 minus sine squared x equals cosine squared x.
Where you get that from?
The first Pythagorean identity.
Very good. So right here, if we subtract sine squared of theta, right? Cosine squared of theta equals 1 minus sine squared of theta. So when we see that, we can change it. So we're going to change that to cosine squared of x, right? You can change that to that. Very good. Okay. Okay, that simplifies it for us a little bit. Now what? Ideas. Not all of you at once, please. What could we do here? If y'all are stumped, then maybe I can help y'all. We had a common denominator, right? So the purpose of what we got a common denominator was to subtract. And so we can leave the denominator as it is and go ahead and subtract the top if we've done all we could with what we have. Denominator the same, and go ahead and okay, that's gonna be sine of x cosine squared of x minus cosine squared of x. Right? Then we're looking at this as a lot going on here. So what can we do? Ideas on what we could do to simplify this. And this is kind of a trial and error process. When I see something, we try something, maybe it works, maybe it doesn't. It's a part of the puzzle. Very good. Kelly says factor out cosine of x at the top. So cosine, well, we can actually factor out cosine squared of x, right? If we factor out cosine squared of x, we're going to get sine of x minus what?
1.
Okay. And at the bottom, we're going to have cosine of x times 1 minus sine of x. We're getting somewhere. Now what? Now what? What can we do here? We're close. We see it. We're almost there. See the finish line. Close, Michael. We can't cross out 1 minus sine of x and sine of x minus 1 just yet. We can do something to do that later. But it would be like trying to cross out 4 minus x and x minus 4. Those are slightly different, right? Because in this case, the x is negative. In this case, the x is positive. But we can do something with that to be able to cross it out. So Natalia says, cross out the cosine squared. Can we cross out the whole cosine square with this? Or you're saying just cross out one of them with this? Just one? Okay. So yes, we can cross out that because there's two of them, right? Cosine of x and cosine of x. We can cross out one of them with this at the bottom. Good. So then that will be cosine of x, sine of x minus 1 over 1 minus sine of x. Okay. We're getting there. Now, I want to play off the idea that what Michael said, to cross out 1 minus sine of x and sine of x minus 1. Let's kind of flip this around a little bit. If we flip this around, it will be negative sine of x plus 1, right?
Multiply
Multiply what?
the bottom one by -1.
Multiply bottom. If we multiply the bottom by -1, we also have to
We
multiply
have to do
the
the
top.
top.
You want to do that? We can try that. So again, it's trial and error. So you're saying multiply the top by -1, like that? Because in order to still equal 1, -1 divided by 1, we're still multiplying by 1. So let's try that. So distributing this to that would be, it will make it what? Sine of x, positive sine of x, and it will make this one -1, right? Would that work?
Why don't we divide by -1 instead?
You could do that. You could do that too. Either way will work, right? So like if we multiply by -1, then we'll have this, and then the -1 is dealt with, and it will cross out. And you have the -1 up here. If you divide by -1, you would divide the -1 out of it. You would end up with sine of x minus 1 as well. And then that -1 would just have to be put up top when you divide it. So either way would work. Very good. So then what we end up with is negative cosine of x. Beautiful. That's what all of that is equal to. And that's how you would simplify it. Get rid of the fractions, use the trig identities in a problem. Told y'all the lesson would be fun for today. Any questions?
Wait, I got lost right there.
I got lost. Let's rewind it back. Rewind it back.
Yes. Okay, so I said like multiply -1, right?
Yeah, let's take this out so we can see it. Let's take this out. Let's take this out. Let's kind of go back to where we started. What was at the bottom here? It was 1 minus sine of x, right? That was where I lost you after that, right?
Yes.
Okay, so you said to multiply by -1 over -1, right?
Yes.
And so if we did that, if we distribute this, we're going to get -1 plus sine of x, right? And that's gone. We have this -1 that we would distribute to that, which give us, wait, yeah, that would give us negative cosine of x at the top, right? And then this sine of x plus 1, and this, I'm sorry, sine of x minus 1, and -1 plus sine of x is the same thing, because if we rewrite this, it'll be sine of x minus 1, right?
Yeah.
So those crossed out,
Okay.
and that's all we're left with. Or we can do the way Natalia said, we could divide by -1, factor that out. You would end up with the same thing. Does that clarify? Did that clarify for you, Anna?
Yes.
Okay, other questions? Okay. Oh, no? Okay. If y'all feel comfortable with that, you can go ahead and we can end it there, and you can do the practice. I'll tell you what the practice is about. If you
We have to go back to.
yeah, I was gonna give you that option. If you want to go back and talk about that problem, or you want to try that problem and then we go over it after, we can do that. I want to be respectful of time, just because I said I wanted to keep it to about an hour, and it's an hour 20. I just want to be respectful of that. So I'll let you choose. How about this? I'm going to say what the practice is, and if you need to log out, you can log out. And then I'll go back for those who want to stay and see that problem, try it yourself, and then we talk about it after. We can do that. So here's because I do want to be mindful of time. I know class is generally an hour 30 minutes, but that includes the practice time. So just trying to be sensitive to that. So for practice, I posted it. Yes, I posted it on Google Classroom. It's in PDF form. There's going to be many different problem types. We have to apply different identities. I would encourage you to help each other offline. Kind of like in the class setting, usually you would work together with your table, and it's really helpful, right? We don't have that now, so I would encourage you to kind of message each other offline. Tomorrow at 10 a.m. is just going to be a question answering day. So bring all the questions that you have from the practice. I know we only had, I think, 3 practices, and one of which I already sent the answers to. So bring your questions for your practice from the practices from last lesson on tangent graphs, and on this lesson, the practice that you work on. 10 a.m. we'll do a session. I'll answer any questions. So be prepared with the questions you already have, and I'll work out those questions with y'all if you couldn't figure any of them out. So that's what it'll be. And then, or any questions about practice or anything like that. So that's kind of for and generally practice. So all practices for the week will be due Friday at 4:20. Friday 10 a.m. session is just a tutoring session. Okay. All right. So if you need to log offline, you can. If you want, I'm gonna pause actually I'll leave the video up. So if you want to work out this problem, you can stay with me and work out this problem. So tell me what you did.
Okay, I'll go.
Yeah.
So what I did was like express the expressions into sines and cosines.
Okay.
So the first one I did 1 over sine of theta,
Mm-hmm.
and then times 1 over cosine of theta.
Okay.
Minus cosine of theta over sine of theta.
Okay.
And then after that, you can pretty much, I multiply the first two, so it'd just be 1 over sine of theta over cosine of theta,
Mm-hmm.
minus cosine of theta over sine of theta.
Okay.
And then I got a common denominator.
Okay.
So I multiplied by cosine of theta.
Okay.
And that would give me cosine squared of theta over sine of theta cosine of theta.
Okay.
And then if you subtract the numerator, it would give you sine squared of theta because of the first Pythagorean identity.
Hold on, let me catch up to you. So you're saying that this gives you sine squared of theta?
Yes.
Okay. Uh-huh.
And then I crossed out the squared and the sine of theta at the bottom,
Mm-hmm.
which would just give me sine of theta over cosine of theta. And that gives you tangent of theta.
Awesome. Very good. You get a virtual ticket.
Yay.
How are we feeling about that topic? Before we close out, any last minute comments, questions, concerns? I think it's fun. Hopefully you enjoy that topic.